as promised, I'm going to go through the rest of these revision questions that we were doing in our revision session on Wednesday, the 19th of January. I won't go through the first question because we have already done that, but I will go through the others now. Okay, so if you can do it along with me with your sheet. So we were talking about this boat, okay, and you drew the free body diagram for it, and then you worked out the size of the weight, or the mass of the boat, sorry. Then it says, when the boat propeller pushes water backwards, the boat moves forwards. The force on the water causes an equal and opposite force to act on the boat. Okay, which law is this an example of? Because the force on the water causes an equal and opposite force to act on the boat, you're talking about two bodies here, the water and the boat. So this is an example of Newton's third law, okay? Newton's third law. Every action has an equal and opposite reaction. Next, figure 3 shows a boat towing a small dinghy. And I've got a bit of a delay on this, 1 second. Okay, hopefully that's sorted it out. And it says the tension force in the tow rope causes a horizontal forward force and a vertical force upwards on the dinghy. So you've got a horizontal force of 150 newtons. Okay, then you've got an upwards force of 50 newtons. Because those two are at right angles, to find the resultant, what we can do is draw them to scale. And on the back, that's what it's asking you to do. So what we're going to do now is draw this to scale and work out the size of the resultant. So we need 150 across and 50 up. So what I need it quite big though, so I can get a nice accurate value for my drawing. So what I decided to do was say, okay, well, if I do 2 centimeters as 50 newtons, that means my 150 newtons will be 6 centimeters. Because that's 150 is 3 times 50, so 2 times 3 is 6. And that will mean my 1 centimeter will be 25 newtons. Okay, then I get to draw that on my sheet, and I would do it in pencil in case you make a mistake, which is what I did several times. Okay, so you're going to draw my first line across, and across is 150, so 6 centimeters. So I'm going to start at a nice point. I'm going to go 6 centimeters and draw my line across, being very careful where I put the end of my arrow. The second force is 50 up, so 50 is 2 centimeters. So I'm going to draw my line up there for 2 centimeters. And then the resultant is here. Now, because it's asked you to do this question by a scale diagram, you would not use Pythagoras to figure out the answer. You would have to do it from your scale diagram. Now, all I need to do is measure the length of this. So that is 6.4 centimeters. 1 centimeter is 25 newtons. So if I times that by 25, it will give me my answer, which I get is 160 newtons. Now, what it would like me to also do is figure out the direction. Now, the direction is this angle here. So you can either measure it with a protractor, which is the easiest way. So take a protractor to your exam. If you don't, you need to use trigonometry. So we have a value here of 150 and one here of 50. So if we're going to find it by trigonometry, you need to do tan theta equals 50 over 150. Now, if you don't know what that means from doing it in maths, take a protractor. If you rearrange this to find theta, you get 18 degrees. Okay, but if you measure it with a ruler, a protractor, you should get that anyway. Next question. Figure 1 shows an exercise device called a chest expander. the 3 springs are identical. A person pulls outwards on the handles and does work to stretch the spring. Complete the following sentence. When the strings are stretched, what energy is stored in the spring? So we would say that is elastic energy. Then we've got the graph shows how the extension of a single spring from a chest expander depends on the force acting on it. So if we increase the force, i.e. we pull the chest expander harder, it extends further. So how can you tell from figure 2 that the limit of proportionality of the spring has not been exceeded? We can tell that because it's a straight line. If the limit of proportionality is met, it means the springs are basically broken and they're all stretched out and don't work anymore, in which case your graph would curve. So we can tell it's not reached its limit of proportionality because the graph is a straight line. Using data from figure 2 to calculate the spring constant of the spring. So the equation we're going to use is F equals Kx, okay? Force equals spring constant times extension. We want to find K, so we rearrange that. So K equals F over X. So we're going to find some values on this graph to do that. So if we look at our graph, our force has gone from 0 to 160. So the difference between those is 160. So I could put my force has increased by 160. My extension, okay, has gone from 0 to 0.4. So I can put my extension in as 0.4. I can then calculate that and I get 400. And the unit of spring constant, well, we've got force, which is newtons, divided by extension in meters, so newtons per meter. Then it says 3 identical resistors in parallel in an electrical circuit share the total current in a circuit. In a similar way, the 3 springs in the test expander share the force. By considering the similarity in figure 2, determine the total force exerted on the chest expander when each spring is stretched by 0.25 meters. If we go back to our graph and draw a line across at 0.25 meters, we can see that the force in newtons that the spring will feel is 100. So one spring feels 100 newtons. But it says in the question that the force is shared by the spring. So if one spring feels 100, the next spring's going to feel 100 and the one after. So because we've got 3 springs, we need to do 3 times 100 and our total force is therefore 300 newtons. Next, the student in figure 3 is doing an exercise called a chin-up. Each time the student does a chin-up, he lifts his body 0.4 meters vertically. So our height is 0.4 meters. The mass of the student is 65 kilograms. And the student is able to do 12 chin-ups in 60 seconds. And it says the gravitational field strength is 10. Now remember, in your exam, it will not be 10. It will be 9.8. But we'll use 10 for this question, even though it's not technically correct. So it wants us to calculate the power. Now, power is energy divided by time. Now our time is 60 seconds. But let's not forget that it does 12 chin-ups. So we need to remember that, the 12 chin-ups. Now, this is not very straightforward because we need to calculate the energy, and the energy that we are using is gravitational potential energy. So we need to calculate that first. Gravitational potential energy is mass times gravitational field strength times height. So we need to calculate that first. So our mass is 65, our gravitational field strength, we're going to do 65 times 10 times the height, which is 0.4. But because so that answer there is 260. But it does that 12 times. We need to multiply that by 12. So 260 times 12 is 3,120. So we can then substitute that back into this equation up here. 3,120 divided by our time, which was 60 seconds. And that's 52. So my answer here is 52 watts. 3 marks for that question. Before a new bus can be used on roads, it must pass a stability test. Figure 1 shows how the bus is being tested. Then it says the bus will topple over if the ramp is tilted too great at an angle. Explain why. Now, an answer to this is always the same. An object will topple if the line of action of the weight. That is a very posh way of saying this line. Okay? The line of action of the weight goes beyond the pivot. Now I spelled pivot wrong. What that means is if you topple the bus so much, I'm not very good at drawing. Oh, I've done that wrong. If you topple the bus enough, that line of action of the weight, which is acting down, goes beyond the pivot, and then it will topple over. So if you want it to stay upright, it can't go beyond this sort of edge of the bus. Yeah, it's got to stay to the left of the bus pivot. Okay, that's always the answer though, if it says, well, why is something going to topple over or not topple over? And it says that the bus is tested to angles of tilt far greater than it would experience in normal use. Suggests 2 reasons why. The first reason might be to find its maximum capacity. This bus is empty. So what we need to do is topple it, do it until it topples, because actually the bus is not going to be full. Sorry, it's not full now, but it might have people in it. So we need to find out what its maximum capacity it can hold is. But what we're also going to do safely is find out its maximum tilt. And we need to check then, we can check then that no roads or anything the bus is going to go over will be at that tilt. Yeah? So you can check the routes to check it's not going to go past something that or over something that tilts it that much. Now, figure 2 shows a hydraulic machine that's used for a ramp tilt. Here it is. It says the pressure applied to the hydraulic liquid at the master piston, which is here, is the same as the pressure applied at the hydraulic piston. State the property of the liquid that keeps pressure in the pistons the both same. It's because in a liquid, force, okay, is liquids exert force equally in all directions. So if you push a force down here with if you push down with a force here, the force up is going to be the same, basically. So force down is going to be the same as the force up here. It says a force of 360 newtons acts on the master piston. Calculate the pressure. Oh, no, it doesn't. It says calculate the force on the second piston. I shouldn't say the force is the same. The pressures are going to be the same, not the force. But that's because force is exerted equally in all directions. So pressure is force divided by area. So whatever pressure we get here is going to be the same as the pressure we get here. So we're going to call this number 1. We're going to call this number 2. So pressure 1 is going to be equal to force number 1, which is 360, divided by its area, which is 0.012. That calculation gives us a pressure of 3 times 10 to the 5 pascals. Now, pressure is the same in all areas. So pressure 2 is going to equal force 2 over area 2. So pressure 2 is the same. So that's going to be 3 times 10 to the 5 equals force 2, which we're trying to find, divided by area 2. And area 2 is given here, 0.28. I now want to find the force, so I'm going to multiply both sides by 0.28. That gives me a force of 8,400 newtons. Is that right? Didn't look right. No, that's fine. Okay. Next. A train travels from A to B. Figure 1 shows the route travelled by the train. Figure 1 has been drawn to scale. Now, the distance the train travels, which is the train route, is different than the displacement. This is the displacement. So the displacement is the distance, straight line distance between the start and the end point. Okay. The distance is the route it actually took. And it says, what is the difference between distance and displacement? Distance is a scalar. So it has magnitude only. Displacement is a vector, which means it has magnitude. So this one has magnitude, size. Magnitude is just a number. Okay. Vector has magnitude, so it has its value, but it also has a direction too. It says use your figure to determine the displacement from A to B. So we want to know how big this is using our scale. The problem is the scale is wrong, so I'll give you both answers. Because this has been shrunk down, this is not 1 centimetre. So it's 0.7 centimetres equals 5 kilometres. So to determine the distance, you're going to be doing 0.7 times the length of this. And the length is 5.2 on my diagram. So I've got 0.7 here. Sorry, I've realised I've missed a step. I need to figure out how far 1 kilometre is. So I'm going to do 0.7 divided by 5. That gives me 1 kilometre, which is 0.14 centimetres. So 0.14 centimetres is 5 kilometres, okay? Is 1 kilometre, sorry. So I'm going to do 0.14 times the length of my line, which doesn't give me right. Hang on, I've done this wrong. Give me 1 second, I'll come. I'm so sorry, I've just realised my mistake. I do apologise. I did this upside down. So what we want to do is if we do 5 divided by 0.7 here, we get 7.1, and then we can multiply our length of our line by 7.1. So 7.1 times 5.2, that gives me a better answer. So that's 7.1 times 5.2, which gives me 36.92 kilometers. Now this would be actually a lot easier if we hadn't messed up this scale. So actually the correct answer that you would get in an exam, because this would be to the right scale, would be you would be doing how long your line was, which was 5.2 times 5. Yeah? Which is probably what you did in this question. Is it 5 centimeters? Yeah, it is. Which is about 26 kilometers. Okay. So both of these are correct. And then the direction is northeast. Northeast. So okay. Then it says there are places on the journey where the train accelerates without changing speed. Explain how. So acceleration is a vector. So you can accelerate by either changing your speed, slowing up or speeding down. So if you speed up, it's acceleration. If you slow down, it's deceleration. But because it's a vector, direction is important too. So if you change direction, you also accelerate. So acceleration is a vector, and the train changes direction. So therefore, we say it accelerates. You look a bit more at that, like in circular motion in the space topic. Then figure 2 shows how the train's velocity changes with time as the train travels along the straight line journey. And it says use this figure to estimate the distance travelled. Now this is a velocity time graph. So the area of a velocity time graph tells us the distance travelled. So we need to figure out what's the area under this graph. So the way I did it was I figured out how much area 1 square, the value of 1 square is. So if we look at 1 square, that's 5. And this is 100. So 100 times 5, which is 500. I then counted how many full squares I had. So if I count these, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I've got 14 full squares. So I can say, okay, well, 14 times 500, which is how the area of 1 square, gives me 7,000 meters. I then need to sort of count up the half squares, and this is where you have to do a bit of guesswork. So I thought if you did this one and this one, they would sort of make up 1 square. So that I did that as 1. I then thought that this one and this one would make up 1 square. And then I just thought, well, at the end, maybe we could just treat this as 1 square, although I think it's probably slightly more. Maybe you would do 1.5 for that. But because you're estimating, you would be given a range. So I think I've got 3 squares there. So I'm going to do 3 times 500. Okay. What I can then do is add those two values together to get my answer. 8,500 meters. Next, the car sees the traffic in front is not moving. What the stopping distance of the car is the thinking distance plus the braking distance. What is meant by braking distance? The braking distance is the distance you travel once the brakes are applied. Okay. The braking distance of a car depends on the speed of the car and the braking force. State one other factor that affects that. Because of F equals ma, it's going to be the mass of the car. Okay. How does the braking force needed to stop a car in a particular distance depend on speed of the car? It's because of the kinetic energy. So kinetic energy is a half mv squared. So if you double the velocity, you've got 4 times as much energy. Okay? And because energy or work done is force times distance, if you've got 4 times the amount of energy, you're going to need 4 times the amount of force to slow it down. Or 4 times the distance. Okay? Then it says figure 1 shows the distance time graph of the car in 10 seconds before the driver applied the brakes. Use the figure to calculate the maximum speed of the car. It'll be where the line's steepest. So get your ruler, lay it down, find where the line is steepest. You've actually got a lovely straight line here. So what I did was just drew that straight line here, and the gradient of a distance time graph tells you the speed. So what I then did was made this into a triangle to figure out its gradient. And the gradient is the change in y. So this goes up from 0 to about 170. And it goes from 10 to 2.6. So 10 minus 2.6 is 7.4. So I know that if I do my gradient, which is the y, which was 170, divided by the x, which was 7.4, that would give me my speed. Because speed is distance divided by time, which is about 23 meters per second. And again, because it's a graph, you'll be allowed a range there. Last part of the questions here. It's on momentum. So the car did not stop in time and it collided with a stationary car in front, and it's really important here that they join together. The momentum of the two cars was conserved. What is meant by the statement momentum is conserved. So conserved means saved. So what we mean is here the momentum before the collision is equal to the momentum after the collision. Then it says calculate the velocity of the two objects immediately after the collision. So because we've said this statement, we need to work out the momentum before. Okay, so if we do the momentum before, we need to do the momentum of the first car times the momentum of the second car. And momentum is mass times velocity. So you get the equation in the exam. P stands for momentum for some reason. So we do the momentum of this car, mass times its velocity. So its mass is 1,500 times its velocity, which is 8. And add it to the second car because there's 2 cars. So we've got 900 times 0, which is 0. So the answer to this is just 1,500 times 8, which is 12,000. Because the momentum is conserved, we can say that the momentum after is equal to 12,000, and that's going to equal the mass after. Now the two cars have joined together. That's really important. So their mass after is 800 plus, oh no, sorry, hang on. 1,500 plus 900. So that's 2,400 times the velocity. So what we're then going to do is figure out the velocity. So we're going to divide through by 2,400. Which is 5. So our answer's 5. Ooh, last question, guys. Bit of a mammoth session. So here we go. Since 1965, all car manufacturers manufactured in the UK must have seatbelts. It is safer for a driver to be wearing a seatbelt compared to not wearing a seatbelt. Explain why. Now, the equation we're going to use for this is F equals mv over t, or change in momentum over time. And the force is the average force. My pen's run out. So the force is your change in momentum spread over how much time you've got. If you wear a seatbelt, the time of the collision is increased. So you increase your time of collision. The change in momentum is the same. Because it doesn't matter whether you wear your seatbelt or not, the mass of the car and the velocity it's travelling at is the same. So that stays the same. So if we increase t, but keep this the same, it means our average force decreases. It's the difference between getting a very, very quick force on your chest, bang. That means that you get all of your force in one go. Whereas if you wear a seatbelt, it stretches, so it spreads that time out. So each second you get less force. Okay, if you've got any questions about these, you can always come and ask me. If going through them you still don't understand something, please come and see me. Okay, thank you.